Cool. Okay. Live.
We're live. Welcome everyone. We're doing live streaming here for the algebra test coming up in MATH1A 3-1. We're at the University of New South Wales. I'm Norman Wildberger.
And I'm Daniel Mansfield. Welcome. You'll have your first algebra class test in your regular algebra tutorial room. Notice that this week there'd normally be no classroom tutorial, but you'll come along just for the exam. So look in your timetable, look for the TU1 time slot and location. That's where your test will be. As usual, we recommend that you bring some paper, some pens, perhaps a ruler for this one, because it is algebra after all. You might need one.
And your thinking caps, of course.
Yes. But you don't need calculators, because most of the numbers will be malleable, and in fact, you're not allowed calculators anyway. Shall we get straight into it? Okay. We've made some selections of just various questions from the sample tests with your assistance as well, so there's been a few requests, and we've honoured those requests where possible. So, the first question. Find a parametric vector equation of the plane in R3 with this Cartesian equation. First of all, I might mention that this bit's normally thrown away, but it actually tells you how many variables you're looking for. So you're looking for an x1, an x2, and an x3. This here is the Cartesian equation of a plane, and we're asked to convert it into parametric vector form. You might recall that is vector x equals the coordinate vector for some point on the plane, plus lambda times some other vector, plus mu times some third vector. And those two last vectors are specify the orientation of the plane, if you like. Good. Well, in this question here, you have some variables, and the way you get this into parametric vector form is to set two of these variables to be your parameters. In this case, I'm going to choose x1 and x2 to be my lambda and mu, and then I'm going to find x3 in terms of those other things. So let x1 be equal to lambda, x2 be equal to mu. Once I've chosen x1 and x2, x3 is specified exactly by the equation. x3 is equal to 7 minus 2 lambda plus 5 mu. Good. So if x1 is lambda, x2 is mu, then x3 must be this for my x, or my point x to be on the plane. So if x, which is equal to x1, x2, x3 is so if in fact this is a point on the plane with this coordinate vector, then I can just write it as x is equal to x1, x2, and x3, where x1 is lambda, x2 is mu, and x3 is 7 minus 2 lambda plus 5 mu. And now I'll just write this out as a sum of three vectors. I'll write this out as 0, 0, 7 plus lambda times 1, 0, negative 2 plus mu times 0, 1, 5, where lambda and mu are just the parameters, any real numbers you like. And now we've converted our Cartesian form of an equation into parametric vector form. A number of you have expressed some wishes to have answers for these class tests that we've put in the back of the book. And no such answers have been given. And in fact, there's a reason for that. Because when you're doing your class test, you don't get answers. You need to come up with your own ways of checking your answers. And in some sense, not giving you answers simulates better, or better simulates what actually happens in a class test. So what's something that Norman and I are going to do in these videos is check our answers. So I have this as my supposed parametric vector form of a plane. How could I check it? Well, I can read off from the Cartesian equation what normal to the plane is. The normal to the plane is very easy to find. It's just the coefficients of x1, x2, and x3. So that's 2, -5, and 1. So at this point the question is over and we're just going to check. Normal is equal to that, and normal dotted with this direction vector here is equal to, well, that's, maybe I'll just write the vector itself, 2, -5, 1, dotted with that is 2 plus 0 minus 2 is 0. Good, and I can check the other one as well. 2, -5, 1, dotted with 0, 1, 5, and that's 2 plus 0 minus 5 plus 5 is equal to 0. Good. At this stage, I'm pretty confident that that is in fact the answer.
The other thing one could possibly check is this point as well, right? This is playing a slightly different role from these two. These are direction vectors for the plane. This is actually the coordinates of a point on the plane. And we could also check that that's on the plane by substituting in here and just making sure that it does satisfy the equation.
And as a marker, I mean, it's a 2-mark question, so as a marker I'd come along and say, I'd look for two things. Have they got a point on the plane? There's lots of points on this plane, but have they got the coordinate vector for a point on the plane? Good. And, I mean, there's lots of possible direction vectors you could have chosen for this. I'd be looking just to check if what they've given me are two non-parallel vectors which are both perpendicular to 2, -5, 1. So really those two things are exactly what your marker is going to do when they come along and see and mark your class test.
Maybe it's also useful to point out that with this kind of equation for a plane, this Cartesian equation is pretty well unique. It's really basically one equation of this kind. But the parametric equation here that Daniel has found is, as he said, just one of many that you could possibly come up with. So what you and your friend got very well might be different, but they still can be right.
Good.
Okay, so this one question here we have to determine with reasons whether or not the 3 points A 3, 5, 7, B 5, minus 4, 3, and C minus 5, 41, 22 are collinear. All right, so collinear means that they actually lie on a line. And I might remark that this notation for a point is an alternative. Sometimes we could also write A equals square brackets 3, 5, 7. That's what we do in our online tutorials more. And this is just another way of specifying the actual coordinates of the point. Okay, so this is a reasonably straightforward question if you know what you're going to do. So you've got some points A, B, and C, and you're not sure if they're collinear or not. What we're going to do is we're going to calculate vectors joining, say, A and B and A and C, and see whether those two vectors are in the same direction. If they're in the same direction, then the points are collinear. And finding out whether two vectors are in the same direction is pretty easy because it's just a question of whether one vector is a multiple of the other. All right, so let's start by actually calculating the vectors. So we'll say we find, say, A, B at first vector. What we need to do is we need to take the difference between the coordinate vectors of the points in question. And I'm going to write that out just to show you what we're doing. So I'm taking the coordinate vectors, or the coordinate vector for B, and I'm subtracting the coordinate vector for A, which is 3, 5, 7. That will then be the vector AB. And we do this component-wise, of course, so 5 minus 3 is 2, minus 4 minus 5 is minus 9, and 3 minus 7 is minus 4. Great. So that's the vector AB. And AC, let's say, is a similar kind of difference between the coordinate vector of C, which is minus 5, 41, 22, and A again, which is 3, 5, 7. Now what do we get there? We get minus 5 minus 3 is minus 8. 41 minus 5 is 36. And 22 minus 7 is 15. So we have these two vectors now. We have to decide, are these multiples of each other? So 2 minus 8, well, if we multiplied by 4, we'd get that. If we multiplied this by 4, we'd get that. It looks like maybe they are. And if we multiply this by 4, we're not getting 15. All right. So these are not multiples of each other. And if we wanted to give a reason for that, we could say since, say, the ratio -8/2 does not equal the ratio of 15/4. And so A, B, and C are not collinear. So we finish up by answering the question directly that we were asked.
I'll just finish writing this question.
Mm-hmm. It's a longer question. So maybe what else could we say about this? You might ask, well, should we perhaps plot these points on a reasonable three-dimensional diagram? Look, you don't have to do that for this kind of question. The beauty of the vector approach to things is that the arguments often work independent of the actual positions of things. So yes, you could draw a picture of these, where these 3 points are exactly, but it's not really necessary. Some kind of heuristic diagram off to the side like this just to orient you, so you're going in the right direction is probably all that is necessary. In fact, the marker is not even going to look for a diagram, it's just going to look for algebraic computation like this.
But a diagram will help you to get all the vectors in the right places. So do a diagram because that will help you in answering this question.
Yeah.
Okay, for the next question we have 3 points from R3 and we're asked to find the coordinates of some other point T on the line AB such that AT is equal to 2TB. You might like to draw a diagram for this. I'm going to straight up just do the algebra of this this question. First of all, I'll let A, vector A, be OA, B, be OB, and I'm going to let T, I don't know what this one is yet, be OT. I'm going to find T. I'm given that AT is 2TB. That means that AT, well that's T minus A, and I know what A is because I've given the point A there, and that's equal to twice TB, so that's B minus T. At this point I have one equation, and there's only one thing I don't know, which is T. So I'll just rearrange this equation so that I find T. I get T, so I'll bring all the T's over to that side, I get 3 of them. And I get 2 B's and 1 A. So that's equal to twice B is 10, 14, negative 4, plus A, which is 1, 2, 3. So I get 3T is equal to 11, 16, negative 1. So T is equal to 1/3 of all that, which is 11 on 3, 16 on 3, and negative 1 on 3. And this is a 2-mark question, by the way. Okay. This is how straight up how I would answer this question. You can go and apply your geometric understanding here. You can perhaps draw a diagram with the points A and B. There's some point T in between them, and the ratio of this length to this length is what they tell you up here. So this length here is twice that length, so it's in the ratio of, let's see, 2 to 1. So you can kind of see from this that T is equal to 2/3 B plus 1/3 A, like that. Which tells you it's kind of closer, it's got more of B in it than it has A. But none of this really, this is nice geometric understanding, but really this is what you do in the question. You don't need to draw a diagram, and in fact I recommend for this question you just solve this algebraically. Norman, do you have anything to add to that? Because I'm about to wipe it off and do part D.
Yeah, look, I think that looks pretty good. We got an affine combination. Yeah, T is somewhere in between A and B. I guess it's, yeah, look, if you actually isolated T there, you have it there, yes. So these are sort of the weightings of B and A in the sort of respective combination. So you can see that T is a little bit closer to B because the weighting here is a little bit more.
Mm.
Yeah. All right, good. Okay, so with this question
sorry,
here...
I've got part B to do.
Oh, you got part B?
It's a two-part question.
Okay.
Two-part.
Please, yes.
Right. For the next question, I'm asked to find D such that ABCD is a parallelogram. So I'm just going to draw A, B, C, and D like this. In this case, I do, in contrast with the previous question, you do really need to put a diagram on to answer this question. I might do some vectors. We know what A, B, and C are, so I'll just label them. Here's A, B, C, and here's a D. And this is supposed to be a parallelogram like that, where that is parallel to that, and that's parallel to that. Good. And I know the vectors A, B, and C, but I don't yet know D. So perhaps I can have an origin over here somewhere, and I know that this is vector A, I know vector B, and I know vector C, like this. But I don't yet know D. What I need to do is construct my vector D, but this is pretty straightforward because I know A, B, and C. And in particular, using those, I can get to D. Notice that this vector here, A to D, is identical to BC. So in order to get from O to D, I might first go up to A and then along by this vector here, which is just the same as BC. So OD, to get to OD, I'm going to first go up to A, and then I'm going to go along AD. But that's just equal to, AD is just equal to BC. Which is, OA is the vector 1, 2, 3, plus BC, which is C, 8, negative 3, 2, minus 5, 7, negative 2. And I might just put some brackets around that. Which is equal to 1 plus 8 is 9, minus 5 is 4, 2 minus 3 is negative 1, minus 7 is minus 8, and 3 plus 2 is 5, plus another 2 is 7. Behold the coordinate vector for D.
Good.
So nothing too strange here. Doing a diagram definitely helps with this question. And then it's just vector arithmetic.
Yeah, I guess one has to also keep in mind, the fundamental difference between the position of a point and the coordinate vector. The coordinate vector of the point A is the vector from the origin, wherever that is. And it's sort of interesting that the analysis here doesn't really depend on where the O is. If you change the origin, yes, these vectors would actually change, but the derivation wouldn't change. It's somehow independent of the origin. Great. All right, so with this question, what are we doing? We've got points A, 1, 2, 1, B is 3, 1, minus 1, and C, 2, 4, 1. And we're asked to calculate the cross product between AB and AC. And then we're asked to find the area of the parallelogram with adjacent sides AB and AC. Okay, so let's get right into it. So AB cross AC. Okay, so this is a test. We want to save time. So let's just write down what these vectors are. We know how to do that. It's the same kind of thing we were just doing before. So we have points A and B. So the vector AB is going to be the difference between these points. So I can just write that down. So 3 minus 1 is 2, 1 minus 2 is minus 1, and minus 1 is minus 2. That's the vector AB. And then I have to take the cross product of that with the vector AC. That's the vector joining this point and that point, so we have to take the difference between these coordinates and these coordinates. So 2 minus 1 is 1, 4 minus 2 is 2, and 1 minus 1 is 0. And I might just check, see if I've done my arithmetic correctly. AB, so 3 minus 1, 2, 1 minus 2, minus 1, minus 1, minus 1, minus 2. Yeah, that sounds right. And C minus A is the 2 minus 1, 4 minus 2, 1 minus 1. It's not bad to check these computations, especially if you're going to use these then to go further. Okay, so now we have to know how to do a cross product. And for that it's useful to remember this kind of mnemonic that the indices here are kind of rotating 1, 2, 3. So the way we, maybe I'll go down here, the way we calculate this cross product is the first entry of the cross product is obtained by, like the top one here, is obtained by taking the second entry here times the third entry here. So there's I'll write it out as minus 1 times 0, so the second entry here times the third entry here, minus the third entry here and the second entry here. So minus 2 times 2. So you can sort of see what products I'm taking there. This times this minus this times this. That was the first entry. Now for the second entry, the next one, I'm going to be taking the 3 and the 1 entries of these two. So I'm going to take the third entry, which is minus 2, multiplied by the first entry, and subtract the first entry times the third entry. And finally, for the third entry of the cross product, I'm going to take the first and second entries of these vectors. So I'm going to take 2 times 2 and subtract minus 1 times 1. So it's the same kind of cross kind of product difference, but we're rotating cyclically through the vectors. You can almost think of this third vector or third component sort of wrapping around to the first one, if you like. Okay, what do we get here actually? So minus 1 times 0, that's 0. We have minus 4 with a minus sign, so that's plus 4. And then minus 2. And here we have 4 plus 1, I guess that'll be 5. So we calculated the cross product of these two vectors. Now, it's a very good idea to check cross products because it's so easy to do that. Okay? The cross product has to be perpendicular to both of these. So we can just do this in our heads. We can just check that the dot product between these two really is 0. So 2 times 4 is 8, minus 1 times minus 2 is 2, it's a total of 10, and minus 2 times 5, that's minus 10, that gives 0. These two vectors are perpendicular as they should be. And similarly, we'll check that the dot product between these two are giving 0. 1 times 4 plus 2 times minus 2 plus 0 times 5, that's also 0. So we've checked that, yes, our cross product is right. Okay, excellent. Now we need the area of the parallelogram with adjacent sides AB and AC. So what we have here is a point A, a point B, a point C. And we're talking about a parallelogram whose adjacent sides are these two sides here. So we complete it like that. Okay. And we need to know that the area of the parallelogram is, well, it's the length of the cross product AB cross AC. It's the length of the vector that we've just found. So that's a square root of the sum of squares, 4 squared plus minus 2 squared plus 5 squared. And that's all together, let's see, square root of 16 plus 4 plus 25 for a grand total of square root of 45. Now we can probably clean that out by taking that square that's in there. There's a factor of 9 there, so if we take that out, make it a little bit cleaner, that'll become 3, and then we'll have 3 times square root of 5. That's the area of this parallelogram.
Excellent. And you sometimes get asked for the area of the triangle, which would of course be just half the area of the parallelogram. Excellent. Very nice. It's important to have some method of remembering how to compute the cross product, so write down the formula and memorize it, or have some kind of tool like this, or determinants if you know how to do that.
Yeah, some of you will have seen the determinant kind of formula, that's also fine.
Yeah. You will need some mechanism of computing cross products, so find one. Good. Norman, I might borrow some of your board to draw a picture.
Please.
So this is a kind of meaty question. This is a 4-mark question. So it's quite involved. We're told that OACB is a parallelogram. We're given the vectors A and B like this, and we're told that A is not parallel to B. All right. And then we have to do things involving these diagonals. So, alrighty, let's put some points on the board and make a parallelogram. Here's an origin, O. There's a point A. Maybe I'll just dry this up a bit more. Let's try again. Origin, good. There's A like that. We're given B, C. So we're given the parallelogram OACB like that, and they have to go in the same order that they were written. We're also given the vectors A and B. So I might pop those on. Here's the vector A to OA, like that, and here's the vector O to B, like this. Alright. We're asked to find parametric equations for OC and AB. This is not the line equation of the line going through A and B. This is just the line, segment A to B and O to C. So, well, I'll leave the diagram over there. That's supposed to be part C. The equation for AB. So let's call this one AB. That's going to be x. Let's give it a parameter t. X of t. How can I describe this kind of diagonal here? Well, one way to describe it is to go first up to A, and then along by some amount from A to B. And that's exactly what I'll do here. That's the vector A plus some amount of the vector A to B, which is B minus A. And t in this case is somewhere between 0 and 1. So that gets me anywhere along this line. So if t is 0, then that just gives me A, and as t increases, it moves towards B. When t is 1, it's B. So here's the diagonal AB. OC. We get OC in exactly the same way. I'll give it a different parameter. Let's call this one S. Now we want this diagonal over here. And I'm going to proceed in exactly the same way. I'm going to pick the coordinate vector for the origin, 0. So I'm going to start here, and then I'm going to move along by some amount of the vector. This vector here is A plus B. So S, A plus B minus 0. So this is some amount of the vector OC. And I can write that out a bit simpler because the origin, this 0 vector just goes away. S, A plus B, where S is an element, again, between 0 and 1. Okay, that's part A. We have parametric equations for OC and AB. Part B now asks you to find the point of intersection of these two lines. So here's another point, P. and we have to intersect them. And you intersect them in the same way that you'd intersect any two objects that you were given. You just set them to be equal to each other and turn the handle. So in this case we have AB is equal to OC, and we get AB is equal to OC. So that's just S, A plus B. And I might organise this so I have the A's on one side and the B's on the other side. So I get the, how much A do I have? I'll bring all the A's over here, and I have 1 minus T minus S. I have that much A, and I have how much B? I get positive S minus T B. Okay, now we've got some interesting equation. We know a few things. First of all, we know these are non-zero vectors. A, B, and C, A and B are not zero. So we might mention that A and B are both not equal to 0 since, well, how do we know that? It's because ABC, OABC is a parallelogram. OACB. Okay, so how else can we make these things equal? Well, what happens if this is not 0? If 1 minus T minus S is not equal to 0, then A is equal to S minus T on 1 minus T minus S times B, which means A is parallel to B. And A can't be parallel to B by assumption, so this thing must be 0. Similarly, if S minus T is not equal to 0, then B is equal to 1 minus S minus T divided by S minus T times A, and A is also parallel to B. Once again, we find ourselves in this scenario where if that's, well, so if that's not 0, then we divide by it and express B as a multiple of A. And we're told that B is not a multiple of A. So, that must be 0 and that must be 0. Hence, let's see, B minus A, 1 minus T minus S equals 0, and S minus T equals 0. Good. So this means S is equal to T. And this one here tells us that 1 minus 2S is equal to 0. So S is equal to T, and they're both equal to 1/2. Good. That tells us that, well, first of all, it tells us that that length there is equal to that length there. Well, actually, that's part C. Let's leave that for part C. In the meantime, we know that OP, the vector OP, is just equal to, well, let's plug half into this equation, is just equal to 1/2 times A plus B. Which is kind of what you might expect. Once you know that OP is half A plus B, then you know, well, again, look, I'm kind of leaning into part C now, so let's leave that. And go on to part C. Okay. Part C. Prove OP equals PC. Well, by part B, we know we know that OP, well actually we know 2OP is equal to OC, because OC is just A plus B. And we also know that OP plus PC equals OC. And that's always going to be true no matter what P is. So, OP plus PC is equal to OC, which is 2OP. And at this stage I just cancel off that with that, and I get PC is equal to OP. So those vectors are equal, and finally PC is equal to OP. What I was asked to prove. So that's telling us that this length here is equal to that length up there. There's one more.
Actually, that was the other ones.
The other one? I've done the other one, thank you.
Yeah.
That length is equal to that length. I'm also asked to prove another relation, and I do it in exactly the same way. So recall that t was equal to a half. In this case we use the fact that s was equal to a half, but now since t is equal to 1/2, I think that means I can get to p by going up here and then along here. So AP was just half of AB, which again means that 2AP equals AB, and I know that AP plus PB is equal to AB. AP plus PB. So to get from A to B, I can go first from A to P and then from P to B. And that's true again for any point P. So AP plus PB is equal to AB, but that's equal to 2AP. And again, I just cancel some stuff off. I've got 1AP here, that'll cancel with that one over there, and I get PB is AP. The question actually asked me for PA. Yeah, what have I done here? PB and PA, yes, good. So now I'll just take the length of these things. PB is equal to the length of AP, but that's also equal to the length of PA. In fact, that's just the reverse of that vector. So we found that that has the same length as that, which is the kind of stuff you might expect of a parallelogram. Good.
Yeah, so that's quite a substantial question there. But you know, it's actually establishing an interesting result that the diagonals of a parallelogram bisect each other. So it's a major theorem of geometry of parallelograms, and this is a proof by the vector sort of framework.
Mm. And we didn't really bring in too much heavy lifting from the world of linear algebra. We didn't use dot products or cross products. We just used vectors and substitution. So this doesn't involve, it's a long question, but it doesn't involve too many technical things that you will have just learned. Good.
Okay, so our last question has to do with projections. So it's let L be the line in R3 through the point P, coordinates 1, 2, 3, and parallel to the vector V equals 3, 1, 2. And now we're also told that let Q be the point with coordinates 2, 4, 4. Okay, so we are asked to first find the projection onto V of PQ. So we're asked to find a projection, one vector onto another. And we're asked to find the shortest distance between the line L and the point Q. And finally, to find our coordinates M of the point capital M on L, which is closest to Q. Okay, so quite a mouthful there. So let's draw a little picture to orient ourselves. So we have a straight line. Can we see that on the? Mm-hmm. Yep, that's good. All right. So we have a straight line, and we have point P, which we happen to know is 1, 2, 3, and 1, 2, 3. Sorry, there. Okay, and we have another point. Well, it's actually also parallel. So we have a vector. We might draw that vector V there. The vector V is 3, 1, 2. And there's our line L. So it's through P and has this vector direction 3, 1, 2. And we have another point Q somewhere. Let's put it up here, which has coordinates 2, 4, 4. And we are asked to find the projection of PQ. So there's PQ, that vector there. We're asked to find the projection of that onto a V. So we're looking for, there's a perpendicular projection there. That vector there is the vector. That's the projection onto V of PQ. And that point that we're going to get, that closest point that's sitting right here, that's the point M that we're after eventually. Okay, so we have to make some calculations here. Okay, so let's get into it. First thing to do is to find this projection of PQ onto V. So we know what V is, we have to find PQ first. So PQ is, well, it's going to be the difference between the point P, which has coordinates 1, 2, 3, so we're wrong way. Actually, let me do it the way I would suggest in a test. Okay? Just cross that out and go Q first. Q is 2, 4, 4. And then subtract P, which is 1, 2, 3. Okay, so we all make mistakes sometimes. So in a test, if you're going to make a mistake, maybe you're writing in pen, you can't rub it off like we can. So if you draw a box around it, cross it out in some reasonably neat way. I'm not sure that's reasonably neat, but anyway. So there's PQ, the difference between 2, 4, 4 and 1, 2, 3, which is the vector 1, 2, 1. So that's that vector there. Okay. And so now we're asked to find the projection onto V of PQ. So the formula for that, which we have to know, the formula for the projection, is it's PQ dot V over V dot V times V. Sometimes it helps to put some brackets around there. So it's some multiple of the vector V that we're projecting onto, and that multiple is obtained by taking the dot product between this vector and that vector and dividing by the quadrants of V dot V of that vector there. Okay, so in our case, what do we have? PQ dot V. Well, V, we remind ourselves, was 3, 1, 2, so I'm going to put that over here. So we're taking the dot product between PQ, which we've just calculated is 1, 2, 1, and 3, 1, 2. So that dot product is going to be 1 times 3 plus 2 times 1 plus 1 times 2. Right? Take the product of the first, and then the second, and the third, and then adding them all up. And the V dot V is just the sum of the squares of the entries. So that's going to be 3 squared plus 1 squared plus 2 squared. And that's the multiple then that we have to multiply V by. And what is this multiple? We have 3 plus 2 plus 2, that's 7 all over 9 plus 1 plus 4, that's 14. So 7 over 14 times 3, 1, 2, which is the same as 1/2 of 3, 1, 2. That's that vector in red there that we have in that picture there. Okay, now we have to find the shortest distance between the line L and the point Q. So we need to find this distance here. That's the distance that we need to find in the second part. Okay, so well, we have this right triangle here, so let me just kind of draw that triangle again to remind ourselves. So we have a triangle there, and we know that this vector here that we just calculated, that one there, is this vector 1/2, 3, 1, 2. And this vector over here that we've calculated, that was PQ, that was 1, 2, 1. That's that vector there. And we're asked to find that length. That's the distance between this point Q and there's our line L through here. So it's a right triangle kind of situation. We could do this in a number of ways, but it's probably nice for us to calculate this third vector. Since we're working in the vector framework, we have two sides of the triangle that we know the vectors of, so this other vector we can find. Let's label this with the point M, which is what it's going to be. So the vector MQ is going to be, this was the point P. So MQ, to go from here to here, we can get there by going from M to P first, and then going from P to Q. Going from M to P is in the opposite direction of this one here, so it's minus 1/2 times the vector 3, 1, 2. And the vector PQ is this vector 1, 2, 1. Let's see if we can do that in our heads. So the first entry is 1 minus 3/2. That will be minus 1/2. And then 2 minus 1/2. That will be 2 minus 1/2. 3/2, yes. And finally, 1 minus 1/2 times 2. That's 1 minus 1, so that'll be 0. So that is the vector MQ. And so the distance that we're interested in from the point Q to the line L is the length of this vector, the length of minus 1/2, 3/2, 0, which is the square root of minus 1/2 all squared plus 3/2 all squared plus 0 squared. For a total of 1/4 plus 9/4, that's 10/4, which I suppose we can write as root 10 over 2. So we found the distance from Q to our line. And the last thing we were asked is to actually find the coordinates M, in other words the coordinate vector M, of this point M here on L, which is closest to Q. That's the point that we get by projecting Q onto our line. Well, we've got everything that we need because we've just calculated this vector MQ. And we know what Q is. and we know what MQ is, so we should be able to put those two together to get the point M. And let's...
And we'll do that just up here.
Great, sure. So that'll then be the final step in this question. Okay, so the third part, to find M, well, let's find the coordinate vector for M. So that's going to be the coordinate vector for the point Q plus the vector Q M. In other words, to get to M, first we get to Q, and then we go from Q to M. So the coordinate vector for Q is 2, 4, 4. And QM, well, we've just found MQ over here. So QM, we better reverse it. So we'll subtract minus a half, 3 halves, 0. For a total of, so 2 minus a half, that's 2 plus a half, that's 5 halves. 4 minus 3 halves, it's like 3 minus a half, that's also 5 halves. And 4 minus 0 is 4. And is that what we were asked? We were asked to find the coordinates M of the point M. So yes, there's the coordinate vector for M.
Cool. I might just mention that there's lots of ways of doing this part of the question, and you can use those to check your answer. So one way is, and my personal favorite way is to do it as we've done here, which is to find the vector, essentially find the vector QM or MQ. Another way is to use the fact that you know this is a right triangle, and you know this vector and you know this vector, so you know their lengths. And you can compute this length here just using Pythagoras' theorem. So that's a nice way to check that you've got the right answer, is just to compute that length there and that length there, and do your subtraction. So this squared minus this squared should be equal to that squared. But again, I prefer this method, especially if you're asked to find M as part 3 in the question. This method involves you essentially doing part 3 as well.
Maybe I should also say, now that I look at it, I see that I could also have found this in another way. Instead of using Q and this vector that we know, we could also have used P and this vector that we also know. That would also be quite reasonable. P is the vector, where was it? 1, 2, 3, and there's the vector 1/2, 3, 1, 2, so we would add those two in the same kind of way. And you could check perhaps that we get the same answer.
That would be another way of checking your working. Okay. You won't exactly be flush for time in your class test.
Yeah.
So quick, easy checks like dot producting, or checking you've got the right normal by just taking the dot product and checking that's equal to 0 is a great thing to do, because it's fast, easy, and it lets you know you've got the right answer.
Yeah. And I guess the place where you shouldn't skimp is when you're actually making a computation and doing basic arithmetic, 3 minus 2. Just make sure you're spending enough time so you write down 1 instead of minus 1 or something like that. So, because arithmetical mistakes will accumulate in a question. They can cause you damage. So when it comes to doing arithmetic, slow down a little bit.
Yeah. And the best way to avoid mistakes like that is to just do lots of questions from the yellow problem book you've got. So the online tutorials are nice because they'll introduce you to the concepts, but for a 20-minute test you don't have time to remember concepts. You just need to be machine-like and churn out those answers. You need to know exactly what you're doing when you see the questions. And that's how you'll do well in the tests.
So good luck on the test.
Yes, and we'll see you next time.